So the first thing to say is I'm still waiting for a couple exams to come back. So I haven't actually formally started grading any of the exams because I'm waiting for a couple exams to come back. But I have looked at all of them, and you guys did great. I mean, like really, really well. My general hope is a decent student will get about half the questions right. And if you know nothing, you'll get nothing right, and a decent student will get about half of them right, and a really good student will get a lot right. And the vast majority of you got a whole lot right. There's none of you need to worry in any way about your grade for the class. It's just a matter of was it a really good test or a really, really good test for you? There was an astonishing number of students who got even some of the harder questions correct. We'll talk about the test a little more in detail when I've actually graded it rather than glanced at it. But if any of you were sitting there nervous that this test is going to affect your graduate career, please stop that. You did well. Whoever you are, you did well. I was really sort of very happy. Does anyone want to ask anything that isn't how to do a problem? I will say also, I embarrassed myself on that exam tremendously. So the most years, in fact, all years, I start with an old copy of the exam and then I modify it and modify it in a way that makes often, particularly in this year, that changes several of the problems and makes, and where I find that previous iterations of the problems had been a little bit poorly worded or the numbers hadn't worked out quite well, I fixed them. And I did that this year too. And then I sent you all the old unmodified exam. So the exam you got was exactly the exam from a previous year with none of the modifications I made for it for this year. So weirdly, also my answer key is totally wrong for this test. So I have to rewrite a new one. But that's neither here nor there. None of you care about those sorts of details. I was just shocked when I got the exam back. It's like, this is not this year's exam. Oh, right. Anyway, that's what happens when you end up like saving things in the wrong directory. I'm sure you've all experienced that effect. Any other stupid class procedural questions before we start thinking about homework? Any other questions of any sort? So this week's homework is homework 7, which has a little bit of selection stuff left over. And then we change gears a lot and go to stuff about recombination. And then we sort of change gears back again and go to stuff about selection and recombination together. Hopefully we'll get through about half the homework today. And at the end of today, I'm going to spend some time talking about some really poorly worded questions on this homework set that you probably couldn't do easily. There was a little bit of read my mind to those questions. And we'll talk about sort of questions 12 through 16 in some detail at the end of today, and give you time if you would like to go back and revisit how to do that little section. But today, hopefully, we'll get through the first, sort of 11-ish problems before I decide my problems sucked too bad to go through them yet, and I need to teach you something. Questions? Okay. Is Linnea on for problem 1? Is she here yet? Don't think she's here yet. Is Carmen? Yeah, Carmen's here. You want to start with problem 1?
Let me share my screen. Sorry, guys. Okay. So This was asking for the, don't remember. This was asking to consider an out of locus. Okay, so what is the ultimate probability of fixation? And I used this equation and just filled in the numbers.
Perfect. Does anybody have any questions about this? You plug in the value of n, you plug in the value of s, you plug in the value of p, and you get the probability of fixation. For those that care, this can be derived from a Kolmogorov backward equation in a pretty simple diffusion model. But for now, we're just going to have you accept that it is correct, that this formula came from God. And but the thing to note about it is, so in this particular problem, we've picked S and N to be, so we've picked it such that N times S is of order 1, that S is 1 over N and S are sort of close to each other. And when that happens, it's not entirely clear what the outcome is going to be. We'll see later that when S is much smaller than 1 over N, things look very neutral. And when S is very much bigger than 1 over N, you get sort of deterministic selection kind of outcomes. But when N and S are near each other, guessing the outcome is not so obvious. And here you find that the probability of fixation of this allele is neither 1 nor 0, or even S, but some little value in between of about 2.5%, which is not very different than its current frequency of 1%, but is certainly higher. Questions about this? Remember, for the neutral locus, the probability of fixation would have been 1%.
I had a question.
Yes.
What happens when the actual population size is nowhere near the effective population size? Like say for like humans, where our actual population size is many, many times greater than the effective population size.
Yeah, so when you go to model that, what you're going to end up having to do is think about like you're going to have to like literally model it over time. So if the effective size, if the world really was that the effective size was sort of the size for a very, very long time, you'll think about evolution as if for a long time it had an effective size that was whatever it was. And then say recently it started growing. And you therefore will start, when you start trying to like understand and model things, you'll model them in a way that for a long time it behaved as if the population was its effective size. But recently, not so much. And you'll start asking what happens to things like heterozygosity over these sort of short time scales where N is much bigger than the effective size. But when looking sort of deep back in time, you'll probably model it as if it were a constant size at its effective size or something like that. You end up with these sort of very odd kind of hybrid models where you sometimes you'll even piece together, like little different time frames and time scales to fully understand them. But as we will see, selection, well, maybe we won't see it as well as we should, but NS like if N has gotten very big very recently, our intuition will be that NS is affecting polymorphism a lot, but not necessarily affecting, say, so the substitution rate in the long term. Does that make sense? Other questions? Up next with problem 2 is Zhengzhi. Is he around? Did you make it?
I am around.
Yeah.
Yes. Okay, so problem 2 was plotting the probability of fixation of the locus, describing problem 1 as a function of p for values of p between 0.0005 and 0.2. So this was just making a plot, and this is what the plot looks like. It looks almost like a straight line when s is a very when p is a very small number.
Yeah. Even not that small. P is 0.2. I mean, P is pretty
Okay,
high.
p is 0.2, not very small. Yes.
Yeah. Yeah, but over anything like any rare-ish allele, it's the probability of fixation isn't that much bigger than the current allele frequency. It'd be exactly the current allele frequency if this were neutral, and even but once you even get to 0.2, it's probability of fixation is only like 35-40%. It's bigger than 0.2, but not crazy high. These sort of NS alleles, NS equal 1 alleles, are not neutral, but they're not dramatically far from neutral. Once they get to very high frequency, the probability of fixation will get very close to 1. But while they're still lowish frequency, their probability of fixation is still not dramatically different than neutral, a little bit bigger. Does that make sense to everybody? So what we've learned in these first two problems is that when NS is close to 1, alleles are not really neutral, but they're not dramatically different. Maybe you can even approximate them with a neutral model vaguely. They're not going to be so different that your intuition is completely radically wrong. All right, up next with problem 3 is Chris.
Okay. My LaTeX is, okay, it's converting now. Okay. Oh, great. Okay, so this is just essentially just kind of a plug and chug. So you take the formula, I believe it was 3.22 in the text. You just kind of plug in selection coefficient and the population size. And when you calculate the arithmetic, it ends up being 0.86.
I'm confused now. Hold on.
Thinking I did this wrong.
I'm looking at my, I'm being weirdly confused at the moment. Yeah, so something went odd in your work there. I'm not sure what it is. Does anybody else, let me see what you've done again. I mean, in principle, what you did is exactly correct. It's not coming out right. So 100,000. I see where it went funny. So what is P in this problem?
Point 0.01.
Why is it 01?
Wait, sorry. I got to refresh my memory here.
It was 01 in the previous problem. What is it in this problem?
Yeah. Well, I don't know. I think I assumed.
What do you think a new mutation means?
Oh, right. Yeah. Right. So it's 1 over to n.
Perfect.
Okay.
Right. Exactly. So let me share with you my screen. So the two of us did it exactly the same way, except my in. Come on. So when are you guys seeing my problem 3? So so when I do it, I'm saying P for a newly arising mutation is 1/2n. I plug into exactly the same formula that Chris did, except for P, I used 1/2n, leaving me with 1 minus e to the minus s on top and 1 minus e to the minus 2ns on the bottom. So I've got the number 1 minus e to the minus s, and e to the minus 200 is the number 0. That is a true-on full 0. So what I have is the answer turns out to be 1 minus e to the minus s. And I have in the back of my head the Taylor expansion of e to the x. E to the x is something like 1 plus x squared over 2 factorial plus x3 over 3 factorial, etc. So if I Taylor expand this e to the minus s, I get 1 minus s plus s squared over 2 factorial, say minus s to the third over 3. Anyway, since this number is 10 to the minus third, the next one is like 10 to the minus sixth, the next one is like 10 to the minus ninth. That number is just very close to the first term. So the probability of fixation of a newly arising mutation is S. Full stop. So Gillespie probably tells you that. So you might have just been able to write down its probability is S. But even if you don't, even if you didn't read, we can now derive that the probability of a newly arising mutation that is additive and whose selective advantage is S, where S is a small number, that probability is approximately equal to S. Does that make sense to everybody? So this is one to have in your pocket forever. This is your intuition for what happens under, sort of, selection and drift. If NS is large, the probability of fixation is equal to S. It's not 1, it's equal to S for large NS, for a newly arising mutation. Does this make sense to everybody? So there it is. That's an approximation that you will, if you end up in a field like molecular evolution, you will use that approximation over and over again the rest of your life, that a newly arising mutation with selective advantage S has about an S probability of fixation. And that's how you want to answer this question if you get it on an exam. Just write down S. Don't bother going through the little derivation. Don't bother showing me, how to Taylor expand e to the x. Just write down the answer is S. Or if H isn't a half, just write down the answer to problem 4, which Mitchell will be up next with. Let me stop sharing my screen. Oh, come on. There it is.
So problem 4 was what is the probability of fixation of an incompletely dominant mutation with the same selective advantage of S equals 0.001 and H of 0.1? So I used this. From the book, I got this approximation, which is just 2 times 1 minus h to the s. So when you get it, I'm missing a point, but I got something about twice of what s was.
Yeah. Or if you want to do it all the way out, 1.8 times what S was.
Yeah.
Yeah. So this is just correct. And what did we learn? That the probability of fixation of an additive mutation is S, but of a nearly dominant mutation. So the heterozygote has fitness much closer to the more fit homozygote. H is 0.1, so that the heterozygote has almost fitness equal to the more fit homozygote. That allele will fix even faster. Does that make sense? That because the heterozygote is being selected more strongly, like the fixation probability is higher. It's probably the way to think about it. But not dramatically higher. It's like twice as high. Questions? All right, up next with problem 5 is Julie.
Sure. So for problem 5, we have effective population size 10,000 and then plotting mutation rate as a function of S. And then we first use the substitution rate equation given in the book. And then it's about 0. We can tell it from the equation. And then when I plot it, so the scale is 10 to the minus 9. So although it looks like 8, but then all of these values are close to 0.
So what was the mutation rate used here?
10 to the minus 8.
Okay, so for a neutral mutation, a newly arising neutral mutation, we think the substitution rate is approximately equal to the mutation rate. So for neutral, so if this had been perfectly neutral, we would have expected the substitution rate to be about 10 to the minus 8th. And show me your graph. So her scale goes up to 10 times 10 to the minus 9th, which is very close to 10 to the minus 8th. So at the sort of far left end of her picture, these are sites that have just slightly less than the neutral mutation rate chance of fixation, which is still very small, 10 to the minus 8th. I mean, or at least of substitution. This is things these are things that will substitute at a rate similar to a neutral site. So these are things at 10 to the minus 8th kind of rate. And very, very, very rapidly, it takes very little selection for that value to go so close to 0. The picture just looks like it's at 0. Pretty, we'll be at 10 to the minus 10th, 10 to the minus 11th, 10 to the minus 12th. We might have been more productive to have plotted this on a log scale, but I think on the linear scale, you see it more sort of fulsomely, that once NS gets much above 10, the rate of evolution gets very low, very fast. NS above 20, don't expect any deleterious evolution. These are deleterious sites. Now we've flipped our signs so that we're talking about the rate of fixation of things that are bad for you. If they're just a little bit bad for you, they can fix at almost the neutral rate. We get almost as much evolution among things that are slightly bad for you as we would for neutral things. But as soon as NS gets out of the NS1 domain and starts hitting NS10, NS20, NS50, there is no chance for deleterious evolution. You can get a fixation of something bad for you if and only if NS is near 1 or close there too. High NS, there's no such thing as evolution. That's a deep intuition for you. So if you think most mutations, say in proteins, are bad for you and that they break the protein, say, and you think in such a way that they have an S that's at least 1% or 10 to the minus third, the kind of S's that Chuck Langley was estimating for null alleles, or HSs that for null alleles, you know those things are never, ever going to fix. Not possible. That only NS in the neighborhood of 1 will allow for the fixation of deleterious alleles, or at least any appreciable evolution of them. Does this make sense for everybody? Okay, up next with the next problem is Sebastian's redoing it, is doing his qualifying exam, is Young Xian.
Okay, let me share my screen, but maybe I don't.
Yeah, I don't think you need to. Tell me about
Yeah.
the generation time effect and what is
Okay. So, okay. So the neutral theory, so like the neutral theory predicts that the organism with shorter generation evolve faster than the organisms with longer generation when the mutation rate is kind of similar across the species. And so this is a generation time effect where like shorter generation, like organisms with shorter generation evolve faster. But this is not well observed in the protein coding regions. Maybe because larger population size, like the organisms with larger population size would like.
Well, let's just stop there.
Yeah.
Let's just stop there.
Yeah.
So we will recall everything we do in this class, more or less, it has a mutation rate per generation. The mutation rate per generation tends to be the natural unit of all the theory. And from a series of experiments in lots of organisms, over a wide range of organisms, the mutation rate per generation appears roughly the same. It appears roughly the same in flies as it does in E. coli, as it does in humans. It's not dramatically different. There's maybe room for 1 order of magnitude difference in mutation rate per generation, but not much more than that. So for the most part, all the theory suggests that the scale ought to be mutation rates per generation of everything, of heterozygosity, of substitutions, of everything, ought to be mutation rate per generation. And so the rate of neutral evolution ought to be proportional to the mutation rate per generation, which is the same in almost all organisms. But time is measured in generations here. So organisms with short generation times in the same number of years have more generations. So they ought to have more mutation accumulate. They ought to have more neutral substitutions in the same amount of time if their generation time is short and their mutation rate per generation is the same. So the neutral theory predicts the existence of a generation time effect. And you can observe a generation time effect, at least in mammals, for say silent sites in non-coding sites. You will see, if you ever look at data, that it appears, say, that mammalian data, that say mice seem to be evolving faster than humans at silent sites and non-coding sites. That's a generation time effect. It's predicted, it's expected. However, there is no observable generation time effect almost ever in protein coding sites, in sites that are replacement, that change what the protein does. So while silent sites often exhibit the generation time effect that you expect them to, sites that change the protein primary sequence almost never do. In fact, if anything, they look like they're evolving at a constant per year rate, which is very odd indeed. Nothing about the theory so far explains why you would get a constant rate per year of evolution of anything. Yet, if you look at protein data, that probably fits that model better than any other kind of model. So this is something, or even maybe quite a bit of a problem for the neutral theory. And we will talk about solutions, possible solutions to it later. But at right now, what we're going to do is say neutral evolution predicts the existence of a generation time effect and observes a generation time effect in non-coding data or silent sites often, but rarely at replacement sites.
Has
Yeah.
anybody gone back and taken a look at the non-coding sites and tried to stratify it by potential regulatory elements, things like that? And maybe
Not so
you might
many,
see
man. Not so many.
an
There may be
effect there.
people doing it now, but not really much. So in
'Cause you
fact,
might, right?
what'd you say?
You could potentially see some sort of effect then, right?
Yeah, easily. In fact, it's so strong. Like if you go and try to align sequence between human and mouse, about the only thing you're going to get aligning practically is the highly conserved regulatory stuff. That the generation time effect is actually so profound, you can hardly align human and mouse in the non-coding regions other than the regulatory. Whereas you'll actually be able to get a fairly decent alignment between human and cows, even though the time back to cow is probably the same as the time back to mouse for humans. But if you look at those early, like multi-species alignment kind of papers, most of those guys didn't understand what they were seeing. But like you will see by eye generation time effect, that things that are a little bitty and evolving really fast, like there's terrible alignments too, and things, big fat mammals that are evolving very slowly, you got great human alignment too, even in the non-coding regions. Other questions about this? Okay, so this is like a sort of interesting, sort of molecular evolution observation that we really do see different time scales of evolution for things that are likely to be less selectively constrained than those that are likely to be more selectively constrained. And in fact, you can observe what you would have predicted from neutral evolution more obviously in the less selectively constrained region, or the things you would have guessed were less selectively constrained. So up with the next problem is Taylor. She's here, right?
Yes, I'm here. So problem 7 is asking us to describe Tomoko Ota's model to explain overall patterns of molecular evolution and what her fundamental assumptions were. So kind of in essence, she's assuming that most protein evolution is deleterious while most silent or non-coding evolution is neutral. And I didn't get it in the book, but I was looking at it online. I think they call this like the nearly neutral model.
We do.
That's cool. Okay, cool. So basically, it relates to what Dave was just talking about a little bit. So we have, if most amino acid substitutions are deleterious, This would essentially increase the rate of what we call effectively neutral mutation, which is where you have a deleterious mutation, but its selection coefficients on the scale of 1/2n. So basically, if most amino acid substitutions are deleterious, I think this would effectively increase the rate of effectively neutral mutation in small populations, and this would kind of offset that generation time effect. But in the case where we have non-coding DNA substitutions, those tend to be more neutral and kind of independent of population size. And so the rate of evolution is kind of what we would expect to be predicted to, which is like dependent on population size and generation time, unlike that of the rate of non-synonymous change, I think.
I think you're getting there. So,
Okay.
so we have one of the two key ODA ideas. One of which is that in proteins, most amino acid changes are deleterious. So amino acid changes that have NS outside the range of sort of near 1 will never fix. So that's sort of part of it. So the only things that we will see fixed between species are those with NS much less than 1 or near 1, but never much bigger than 1. So that's part of the theory. So what we expect, therefore, is organisms with larger N will have fewer potential sites that could be fixed. If we think that S is a property of the protein itself, like if you break a protein, it's bad for you no matter what the organism is. If S is a property of the protein, populations with bigger N's will have fewer sites that could fix between species. So larger N will equal fewer potential sites to fix in sort of fewer overall substitutions. That's sort of the one bit of it. Bigger N means fewer nearly neutral sites. The other piece of her hypothesis was something that is actually kind of true. Let's imagine for the moment that organisms with long generation times also have smaller population sizes. Other than humans, in the vast majority of mammals, that's sort of true. Elephants that might live 50 or 60 years, there are hardly any of those. We might be able to count them by name. Gorillas who have generation times not that dissimilar from humans, again, we could name them all. There's only 5,000 or whatever of them. Very, very few. On the other end, there's, maybe thousands of mice, maybe hundreds of thousands of mice, maybe millions of mice living in Lowwater Park. That mice populations tend to be very, very large. And as anybody who knows, sort of who does any mouse breeding, a mouse generation time isn't even a year, probably. It's probably less than a year. So at least for mammals that we have some intuition about, large mammals with long generation times do tend to have smaller population sizes than little mammals with quick generation times. And that may be true across a lot of organisms. So what we have is those organisms with large population sizes have fewer effectively neutral sites, so that there are fewer sites that could fix between species. But those organisms with large population sizes also have short generation times, so that the neutral things ought to be evolving faster, because we expect the amount of neutral evolution to be proportional to the mutation rate per generation times the number of generations So Oda's hypothesis is that things with large populations have fewer sites that could evolve, fewer effectively neutral sites, but those effectively neutral sites are evolving faster because they have shorter generation times. And it has, and by sort of magic, the size of these effects have canceled so that there is no generation time effect in proteins. It's a very, very imaginative hypothesis. In detail, when you start modeling it, you can make it go down the road so that you largely get rid of generation time effect in proteins while keeping it in things that are more neutral. Unfortunately, you can get it to go down the road, but it requires some carefully, some precise assumptions on the distribution of selection coefficients. And something like the variance in the distribution of selection coefficients times n has to be of order 1. So you don't fully get around this problem, but it largely does. NS now, if the variance in selection coefficients is of order 1, you can probably make it all work. And that is Oda's nearly neutral explanation for generation time effect in one set of sites, but not others. Do we have a question about this? Up next is Kevin with the next problem.
Yep. So let's see.
Changing fields entirely.
Yep. So in Gillespie, it says that this equation, which is what is the basically the frequency of a locus with multiple alleles on it, can be understood best from like making a statement. So he basically goes and like says like, this is the probability that it's non-recombinant. This is the frequency of A1, B1. And then, you know, he goes and described all this. So I basically just rewrote it from that statement for all 4 of those things. So
yes,
yeah,
yes.
So yeah, just using I think there's actually like somewhere in Gillespie, there's actual references to like what P1 is, what Q1 is, but yeah, it's I just basically took this from more or less the book.
Yeah. So the expected frequency of an A1B1 haplotype, chromosome, gamete, they're all the same word here. They all mean a piece of DNA with 2 different sites that you can observe on it. The frequency of an A1B1 haplotype next generation is equal to its frequency this generation times the probability there was no recombination between the 2 sites, plus the probability there was a recombination between the sites times the probability you'd get an A1 at random with a B1 at random. And the frequency of all the other gametes, all the other haplotypes, next generation, the expected frequency is the same in the sense of it's 1 minus the recombination rate times the current frequency plus the recombination rate times the underlying allele frequencies. Does this make sense to everybody? So what recombination is doing, I'm not sure if I made you plot this over time, but if I had, you can sort of imagine that no matter what the current haplotype frequency is, every generation, it gets closer and closer to the frequency of one allele times the frequency of the other allele independently. That The current frequency gets decremented by a value 1 minus R, and you get R closer to the independent allele frequencies. So that recombination tends to break up association between sites. And if you allow recombination to act long enough, eventually the sites are effectively independent, and the frequency of a A1B1 gamete is the same as the frequency of A1 times B1. Does this make sense to everybody?
Can I ask one quick question about the A1B2? Because
Yep.
I wrote it down on my homework, but then seeing it on Kevin's and then seeing it on mine, I wasn't really sure. I think the formula was 1 minus R X.
Just show me what
two-
you got. We'll talk through yours.
Sure. It's just really which when to include. Sorry, share screen. When to include the Q1 versus Q2, and I think I had done going on a journey. Here we go. So right in this part, which I had actually made a mistake here, but that's okay. The focus is on this part of the term, which is the Q1.
So
Should it actually be Q2 or?
no.
No.
It should be
Okay, I didn't
Q2. Yes, it should be Q2, the way
Okay.
you have. So again, there are lots and lots of ways to denote these things. And this notation can get very annoying at times. And it's very easy to switch what you mean by 1s and 2s, A's and B's. And so the way I think you have this written is the frequency of A1 is P1. The frequency
Yep.
of A2 is Q1. The frequency of B1 is P2. The frequency of B2 is Q2.
Correct. Yeah. Yes.
This would be P1 corresponding to an A1 and Q2 corresponding to a B2.
Yeah. Okay.
But regardless of how you've assigned your P's, your Q's, your 1s, and your 2s, the intuition should be obvious. Its frequency next generation of the gamete is the frequency this generation of the gamete times 1 minus R, the probability of no recombination, plus the probability of recombination, and then randomly sampling the two gametes according to their frequency. No matter how you choose to write it, it should always be gamete's frequency next generation looks like the gamete's frequency this generation times the probability of no recombination plus the probability of recombination times random sampling of the two gametes according to their frequency. And again, that intuition is super easy. Sometimes getting the notation correct can be a pain. And more often than not, when you make an error here, it will be not in the understanding, but it will be in you got yourself confused as to what's a 1, what's a 2, what's a P, what's a Q. And I would say we all do that. It's rare for that to stay clean and correct every time, all the time.
Going forward with our example here with A1 and B1, are we saying that the A1, B1 is a non-recombinant and the A2, B2 is a non-recombinant, and then the mixtures are recombinant?
Oh
That's
God,
example?
I hate those words. I would avoid those labels full stop.
Okay.
I would simply say A1, B1 is a haplotype, and the what you want to call recombinant and not recombinant will have a lot to do with the history of the alleles. And we tend to use those words recombinant, non-recombinant to mean haplotypes that existed when the alleles entered the population, first entered the population, versus haplotypes that were only came about after that first generation due to recombination. If we really wanted to go into this stuff, you could quickly prove that for 2 sites, the number of haplotypes are either 2 or 3 in the absence of recombination, depending on how you drew the tree and where the mutations arose. That there will be only, when you have 2 sites with 2 alleles, there can only be 2 or 3 haplotypes. So the 4th haplotype coming into existence is a proof there has been recombination between those sites in their history. And depending on, and it's possible there are even 2 haplotypes that could only have been created by recombination, depending on where the mutations arose in the tree. So I would prefer never to call a haplotype recombinant or not, unless I am fully writing down a picture of a tree and I have some hypothesis as to which allele arose when, who came first, and where in the tree they are. And then we can start talking about that stuff. Until then, I'm not going near there. And as we're going to see in the next problem or two, you can't even reasonably talk about the sign of disequilibrium. That the sign of disequilibrium is a function of how you've labeled the alleles. And although some of us might choose to usually label the alleles as commons and rares, there's no guarantee the next guy did that too. So there's like no guarantee the sign of D is going to make any sense to you. And you're going to have to be really explicit about stuff if you want to try to understand that. Other questions? All right. Oh, hey, man, by chance, up next is Jim.
Oh, great. Okay. So, arithmetic is not my thing, so this is maybe not the best for me, but I kind of took a couple of shortcuts. The problem was, we're on 9, I believe, right?
Oh, yeah.
The problem was basically asking us to play around with some of the definitions of D and the allele frequencies and kind of plug them in and interchange with each other. So the first part of the problem was asking to show the gamete functions as a function of D are correct. So this part, and to do that, we know this, and we also know that D is equal to this. So you can plug in, in for D into the, this part, and you get a whole bunch of things. And, you guys probably did the simplification of it all, but I kind of just took it for granted.
Yeah.
And assumed that it does cancel out just x2.
So let me show you I have not even you can actually show this without even bothering to assume this D equals x1 minus x2 times x3. I'll show you the algebra.
This is that, yeah.
It's both easier and harder than you have, maybe. Or not harder, but just different. Let's put it that way. I can share my screen. I really can.
Sure.
Share screen. So for problem 9, it's actually it's almost super fast just to go back to the definition. So the definition of D is x1 I have, so X1 is the frequency of an A1B1 haplotype. And one of the ways to define D is to say the frequency of A1B1 haplotypes is the expected frequency of A1 times the expected frequency of B1, which I've labeled P1 and P2. So this is the sort of, sort of random sampling plus some amount of disequilibrium. But if you guys will remember, X1 is the frequency of A1B1. X2 is the frequency of A1B2. So the frequency of the A1 allele is X1 plus X2. So P is equal to X1 plus X2, or X2 is equal to 1 minus X1. Now I've done nothing more than taken my X1, which is equal to P1, P2 plus D, and plugged it in there. Now I factor out a P1, and I get P1 times 1 minus P2 is equal to minus D. So that's P1 Q2 minus D equals X2. Now, again, by a similar logic, P2 is defined as the frequency of X1 plus X3. So X3 equals P2 minus X1. So plugging in for the value of X1 again, I get P2 times Q1 minus D. X4 is equal to the frequency of Q2, or Q2 is equal to the frequency of X2 plus X4. So 1 minus P2 is equal to that, and you get Gillespie's formula. For the value of D, to show that D is equal to that cross product D-type term, I've done nothing more than plug in these values, plug, 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 and you can start finding Q2s plus P2s, P2s plus Q2s, those are ones, then you get a Q1 and then you get D. Just algebra and definition. But what we used is the fact that the frequency of the allele looks like the sum of two haplotype frequencies. That sort of makes the algebra go easiest. There are, I'm sure, hundreds of other algebraic ways of getting to this answer, because it's all true every which way you look at it. But I think this is probably the simplest algebraic approach. Questions? And that was, and this is nothing more than algebra, and it is just showing you that all the different, so let's just talk about this now. So why did we bother to do this? What it says is we first define linkage disequilibrium in terms of the difference between the observed A1B1 haplotype and the expected frequency of A1B1 if there was just random sampling. And we got that was the value of D. That was the difference between those things. But there's nothing special about A1 and B1. Why didn't we do it in terms of A1 and B2, or B2 and A1, or B2? All four ways of defining that we could have defined D results in the exact same value of D up to a sign. So if you change the allele you call A1 versus A2, change the allele you call B1 versus B2, you shall arrive at the same value of linkage disequilibrium up to a sign. The sign tells you nothing other than how you labeled the alleles. It does not give you any insight into anything other than that was how you labeled the alleles. And if someone got a different sign, they labeled them differently. So the sign is telling you nothing. And And there are loads and loads and loads of ways of calculating this value of D from the difference between the observed and expected frequencies of a haplotype. Are there questions about this? All right, up next is Brooke with problem 10.
Okie dokie, 1 second while oh, this one, okay. I don't know why I always struggle a little bit with this, so I will.
Ah, this, good.
Okie dokie. Doo-doo-doo. Okay, so we are tasked
We
with.
didn't struggle in any way, shape, or form.
Okay, well, that's good. I may then pardon my explanations. Okay, so we're tasked with finding the expected values for the A locus, I guess. And then also the variance for each of these. And they're really, because they're independent, they should really look like each other, I think, quantitatively, which is what I ended up trying to show. But basically, it's just using the definition that we know and love for expectation, which is the probability times the, what was it? Probability times the value. So we know from the equation that anything that's labeled as A1, it's going to have a value of 1. If it's A2, it's going to have a value of 0. So I set up the probability so that the probability of A is this, and when it's A1, it's times 1 plus the Q value, which is going to be 1 minus P times 0, which ends up with your PA value. And then the variance is just going to be also based on the definition of variance. And then it looks the same for the expectation and the value of B.
Yeah, that's exactly right. So if we think of this A1 locus as nothing but a Bernoulli random variable, where one of the alleles is labeled 1, the other allele is labeled 0, the expected value of the A random variable is the frequency of A1, P. The variance is PQ. Same thing for B. The expected value is the frequency of the B1 allele, PB, the way we've labeled it here. And the variance is PB QB, or 1 minus PB, depending on how we've noted it. And this is 100% perfectly correct. So and again, it may have seemed incredibly stupid and a waste of your time to have done, except Michelle, now let's do the next problem.
Okay, so I definitely made a mess out of the next problem. But you can look at my mess. Share my screen. Okay, so we're finding the covariance and the correlation of A and B. So covariance is
you've gone to like a count rather than
so
frequency.
Count, which gave me a bunch of n's that I don't know what I. Yeah, so this is the equation for covariance, and then finding the expectation of A times B always like breaks my mind a little bit. So I'm not sure this is right, and I switched it to counts.
Yeah, this is all kinds of confused, but is absolutely on the right track. Let me show you mine. Yeah, but this is exactly right. This is exactly what I wanted you to do. But let's get it quite right. And let's see. Why am I so bad at this? Share screen. Okay. So problem 10, we had the means were PA, PB, the variances were PA 1 minus PA, PB 1 minus PB. Now we get to problem 11, which was the reason I made you do problem 10. So what I want is, so the covariance of A and B is equal to the expectation of A times B minus the expectation of A times the expectation of B. I probably should have done, oh, I did do this out for you. Only I wrote it in the text so that it was hiding. So what is the expectation of AB? It's the probability both A and B are ones times the value 1. Because when A and B are both 1, that's 1 times 1, or 1. So it's the probability both A and B are 1, plus the probability A is 1 and B is 0, or the probability B is 0 and A is 1, or the probability B is 0, A is 0, times something times 0. So this expectation, the expectation of AB, is equal to the probability A is 1 and B is 1 times 1. And that probability we've been writing as either x1, or in this case, I wrote it as the frequency of the A1, B1 haplotype. So the covariance between A and B is equal to the frequency of the A1, B1 haplotype minus the frequency of the A1 allele times the frequency of the B1 allele. X1 in Gillespie's notation, PA1, B1 in my notation here, minus the frequency of the A1 allele times the frequency of the B1 allele. That's D. The linkage disequilibrium D is nothing more than the covariance between locus A and B if we label one of the alleles 1 and the other allele 0. If we think of this as two Bernoulli random variables, Bernoulli random variable A and Bernoulli random variable B, the covariance between those two random variables is the amount of linkage disequilibrium between the two sites. That's a sort of deepish idea. D, linkage disequilibrium, defined, God knows how long ago, well over 100 years ago, is actually nothing more than the covariance between the two sites when we define one of the alleles as 1 and one of the alleles as 0. The correlation between those two sites is, by definition, the covariance divided by the square root of the two variances. The covariance is D. As we saw from the previous problem, the variance looks like PA 1 minus PA, PB 1 minus PB. So the correlation is nothing more than D over the square root of all the allele frequencies. So the squared correlation, which we often write when doing like regressions as R squared, is equal to the covariance squared over the square root of all the variances, which here is D squared over all the allele frequencies. Thus, the linkage disequilibrium R squared is nothing more than Pearson's correlation coefficient squared, where I've labeled the two alleles 1 and 0 at each locus. Does that make sense to everybody? This is how you should internalize linkage disequilibrium. The D value is just the covariance between the alleles. The R squared is your R squared value. It's like it's just like any old regression. So, and when we're in some modeling kind of framework, R squared is going to feel like the variance explained. And therefore, our tests of significance are going to look like R squareds times N. But we'll get to that in a little bit. But is this all clear to everyone? That we start with something that seems so easy that it's hardly worth having done. We label A11, we label A20, label B11, label B20. We ask, what is the mean value of my A random variable? What's the mean value of my B random variable? What are those variances? And we just get P's. Then we ask, what is the covariance between the two loci? And we find that it's equal to the frequency of the haplotype minus the expected frequency of the haplotype when they're unlinked, which we've previously defined to be D. D is the covariance. So therefore, that's the correlation. And this is the most natural way to think about linkage disequilibrium, is in terms of something like the variance explained by the regression. Up next is Kiana with problem 12. I think 12 is still doable, right? Yeah, more or less. Kiana with us? I haven't actually seen her. No Kiana? Oh, no Kiana. Oh, but Linnea's here now. We skipped you early. Do you want to do the next problem?
Sure, sorry about that. I totally slept in.
No, these things happen.
Let's see. 12, I think, right? Yeah. Okay. Yeah. Okay, so I just plugged in the values basically into the D and R squared.
Good.
Yeah.
And so what value did you get for D?
End up with 1/100th.
Good. And what value did you get for R squared?
2, I guess 10,000ths. Or wait, sorry, it's 2,000ths, my bad.
Yeah, something like that. Yeah.
I can read zeros.
I think I got 2.26 thousandths, but I probably rounded a little less than you did. But yes, this was just a, can you plug values in? Have you understood all of the things well enough to plug values in? And you should have gotten 1% for D, and you should have gotten like 2 times 10 to the minus third for R squared. Does anyone want to talk about whether they got something different and to look at it? And you probably could have found other ways of plugging in values to find D, but that is certainly a good enough formula to have used. All right, let's see. Let's see. Okay. I'm sorry. What did I actually? Yep. Okay. I thought I saw Kiana there. Are you here? Do you have sound, Kiana? Maybe? Nope, she's gone again. All right. Her internet connection obviously sucks. Okay. Mega, do you want to try the next problem?
Yeah, I can do it.
That is the last one we will try today.
Okay, so for 13 down here, it really just asked what population size was necessary for it to be different. And they already told us that the degrees freedom was 1 and the p-value, so I just looked up the critical chi, and then I kind of just plugged in our R value from the previous one into the equation that was in Gillespie,
Yep.
and solved for n.
So something like that looks pretty good. What did I get? Yeah, I got the exact same number. 1693.44. Yeah, 0.88. Okay, yep. Exact same number. Okay, so this NR squared is one of the standard tests of significance for a squared correlation coefficient. In almost all circumstances, the one test for whether two variables, a simple test for whether two variables are correlated statistically, is to calculate R squared between them and ask whether the sample size times R squared is bigger than a chi-squared with 1 degree of freedom. And it's really sort of asking whether the variance explained here is significant. It's really sort of the way to think about it. It is not always, it is actually seldom the most powerful way you can test for significant association, but it is a robust test. And if NR squared is statistically significant, these two things are correlated with one another. They are not independent. You've rejected independence pretty strongly. And you will, well, maybe we'll talk about it as we go. But so when thinking about linkage disequilibrium, when thinking about whether or not you think two sites are correlated with one another, the way you want to decide that is you calculate R squared between them, and you ask whether your sample size in chromosomes is such that R squared times your sample size is a number bigger than something, bigger than 4, bigger than 10, bigger than 30. If it's bigger than 30, you know, like it's genome-wide significant associated. It's bigger than 10, you know, it's like 10 to the minus third. If it's bigger than like 4, you know, it's bigger than 0.5, you know? So in your head, this is how you should be scaling linkage disequilibrium. R squared times your sample size. If that number is a biggish number, these things are highly correlated. And the reason that's your test is because that R squared, which we wrote down as D squared over all the allele frequencies, is actually the squared Pearson correlation, is actually the square of the Pearson correlation coefficient for the two Bernoulli random variables. This is not, you know, they are the same. This is the right way to think about it. Any questions about this so far? And we're going to stop here for now. And I'm going to talk about the next 3 or 4 problems, which pretty much made no sense because I didn't tell you enough for them to make sense. And I would like to go through them a little bit so that they become less a guess what the hell he was thinking and more trying to understand something deep. So problem 13 we just did. We saw, you guys can all see my screen, right? So we saw that the way to ask whether or not these are statistically correlated, these two sites, is to calculate R squared between them. multiply it by n, and ask whether n is whether nr squared is a big number or not. And for any n bigger than about 1,700 chromosomes, you would have concluded this was statistically significant LJ. So the first thing we should probably talk about before we talk about the mechanics of my crazy problem is a statistical test for whether or not an allele is associated with disease. And the most natural test on earth is a sort of 2x2 test where you sort of think of your two alleles, we'll call them B1 and B2, and you count up the number of B1 alleles in cases, you count up the number of B2 alleles in cases, you count up the number of B1 alleles in controls, you count up the number of B2 alleles in controls, and you ask whether this ratio, say the number of B1 alleles in cases to controls, is equal to the same ratio of B2 alleles. Or maybe thought the other way around, the ratio of B1 to B2 alleles in cases, whether that ratio is the same as the ratio of B1 to B2 alleles in controls. And the simplest test of these sort of 2x2 tables would be a chi-squared test with 1 degree of freedom. And what you would do is you'd have your observed counts here, the observed count here, the observed count here, the observed count here, the observed count here. And you would ask whether these observed counts were consistent with an expectation of the count being something like the overall frequency of B1 alleles times the overall frequency of cases times your sample size. That would be your expected, and then you'd write down the chi-squared. But I will tell you, and this is a nice formula to remember for the rest of your life, and you'll see certain similarities to this, to what you've already seen, that this chi-squared test statistic can be written, again, these are observed counts, as this count times this count minus this count times this count, quantity squared times the total sample size, the total count of the table, divided by the sum of that row times the sum of this row times the sum of this column times the sum of this column. That you can write down the expecteds, take observed minus expected squared over expected, summed over all 4 boxes. I could make you prove, but I will not, that the answer you get is going to be this number times that number minus this number times that number, quantity squared, total sample size on the outside, all the columns and rows as the denominator. That is the simplest test for association. And this thing may very well dramatically remind you of the linkage disequilibrium test you just did, where instead of B1, B2 cases and controls, we had B1, B2, A1, A2 here. This chi-squared looks preciously like this chi-squared is not a coincidence in any sense. We have effectively relabeled our A locus cases and controls and done the exact same thing we did here on this problem. This is not a coincidence. But this is also the standard test of association that, like every single software package does. That when you ask for whether There are other versions of this, but when you just do the simple allele frequency test, you do a chi-square test with this sort of 2x2 table. So the first problem here asks you to find a value of the sample size. Oh, by the way, nothing about this problem implied you had to have an equal number of cases and controls. That was just stupid on my part. I should have required you to have the same number of cases and controls. If you want to, you can solve this for unequal cases and controls. That's fine too. But some of the beauty of the problem is it becomes even messier when there are unequal cases and controls. Just please assume there are an equal number of cases and controls. In the way I've written this, there are n cases and controls. If you write it down as n cases and controls, you'll just follow my math and get something that looks almost neat. But the problem asks you to find a sample size so that this chi-squared value is significant. And that'll be straightforward for you. Problem 15 is where it all is even weirder in terms of what the hell was he thinking and talking about? So the way, this is actually kind of how the world is, right? Certainly for any sort of disease that is slightly uncommon. You can sort of think of the world as being made up of chromosomes, in this case, haplotypes, that are disease-free. And that's the way the world is. And there's a much rarer chromosomes, haplotypes, that have an allele on it that causes disease, or at least contributes to disease. And the sort of way you should think about how to sample disease alleles is a lot like just sampling control alleles, but oversampling, picking the allele that contributes to disease more often than you should by chance. So in this little toy problem, the B2 allele was at frequency 30% in the general population in controls. But the problem asserts it is at frequency 50% in cases, presumably because it causes disease, or at least contributes to disease. But if the way we get chromosomes, the way we get haplotypes, is by pulling haplotypes from the control population, but with just simply biased sampling of B2 relative to B1, the result of that will be the marginal frequency of the A allele, given whatever B allele you have, will be the same in cases as in controls. So if I know the allele is a B2, the frequency that the other allele is A1, if I already know this site is B2, will be the same in cases as in controls. So the probability that you get in A, for any I or J, the probability that you get an I allele, given that you have a BJ allele in cases, is exactly the same as the probability you would have gotten an I allele, given that you had a BJ allele in controls. So to get all of the haplotype frequencies, I'm going to use Bayes' theorem over and over and over again. So Bayes' theorem is the probability of an A and a B is equal to the probability of A given B times the probability of B. So the probability of AI, so let's be a little bit specific here. So, so first though, I've asserted to you that the probability of this conditional probability of A given my B allele is the same in cases as in controls. let's first find what those values are in controls. So again, from Bayes' theorem, the probability of A and B is equal to the probability of A given B times the probability of B. Therefore, the probability of A given B is equal to the probability of A and B over the probability of B. So the probability of an A1 allele given a B1 allele in controls is the frequency of A1, B1 haplotypes in controls divided by the frequency of B1 alleles in controls. 0.05 divided by 0.7. We've already had those numbers. The frequency of A2 alleles, given that you are a B1 allele in controls, is the frequency of A2, B1 haplotypes in controls, divided by the frequency of B1 alleles in controls, and so forth. The way I'm sampling, these conditional probabilities will be the same in cases. So these are also the conditional probabilities in cases. So I can find the frequency of A1, B1 haplotypes in cases by using the conditional probability I found up here, times the frequency of B1 alleles in cases, times the frequency of B1 alleles in cases, and from here get my frequency of my A1, B1 haplotype, A2, B1 haplotype, A2, B2, and A2, B2 in cases. And then I ask you to find D and R squared in cases, straightforward. Then I ask you to do the exact same association problem with A1 alleles, the A alleles rather than the B alleles. And you will find you're able to do that. Does this make sense? So there is a lot of Bayes' theorem being done right and left here. We're going to use the probability of A1 and B1. The haplotype A1, B1 is the probability of A1 given B1 times the probability of B1. Various different ways around. And it's the fact that we've sampled controls in a biased way that's what's forced the marginal probabilities to be the same.
I have a question
Yep.
about that. And for number 16, so I used the result that if you do a chi-square test of association with the true disease variant, and you get a test statistic chi-squared, then your chi-squared test statistic for a variant in LD will just be R squared to chi-squared. Is that an appropriate approach?
That might have been what you learned.
Yes.
From this problem. So, because you are already a card-carrying genetic epidemiologist doing your own work, biostatistician for that matter, that you actually know this. You have internalized this result so well, you didn't actually have to go through and do it. So it is utterly appropriate that you jump to the answer, and you would have found that it's true.
I have a question about that then, because when I did it, I went back and I was unsure, because if that's the ending result, the R squared value, since technically we're testing a population that's half controls and half cases, we showed that the R squared is different in the control population, the disease population. So is the R squared like the average R squared between the two populations?
It's much closer to the R squared in disease populations.
Oh, okay.
Neither one are exactly correct. And if you had, in fact, when I go through and do it, I will show you that the R squared in the control population is about 14% off. The R squared in the disease population is like 1 or 2% off. It is not exact, but it is so close that you will internalize that result and approximate it that way the rest of your life.
Thank you.
But that's what we're going to talk about next time. But yes, so here's a hint, guys. the chi-squared value you get in problem 14 ought to be the chi-squared value you get in problem 16, but off by a factor of r squared. And that's what we're going to talk about next time for most of this this time. So are there any further questions on this homework? We'll go through them, and I'm going to give you guys, particularly those of you who like want to be or are human geneticists, I'm going to give you a chance to sort of look at these and think about them yourself between now and Thursday. And then we will go through them and do them again in some detail on Thursday. And then we'll talk about homework 8, if you have any questions there. Yeah, I guess that's about that. Any questions for now? Okay, I will see you guys Thursday.